When I talk about factorising vectors, I'm really only talking about taking out common factors, just as we do with algebraic expressions. And as we're not into multiplying vectors by vectors, the only common factors I'll be able to take out are scalars. In other words, simple numbers like a third or 5. And that makes this aspect of the work extremely simple. But let's start by multiplying a combination of vectors by a scalar number. For example, suppose we calculate a certain vector to be 3a plus 5b using the lowercase notation. A vector 4 times as long will be 4 into 3a plus 5b, and we can multiply this out. So we can write 4 into 3a plus 5b is 12a plus 20b, just as you would expect. Similarly, if we are given a vector combination such as 16d minus 12e, where d and e are vectors, we can take out the common factor 4 and write 16d minus 12e equals 4 into 4d minus 3e. As before, this is the sort of thing we're used to doing with normal algebra. So let's use this idea in an example. Suppose we have this diagram. The vector QA is small a, the vector QB is small b, and C is the point 1/3 of the way between A and B, i.e. the length BC is twice the length CA. We're required to find the vector QC in terms of A and B. Now, if QC is the low road, what we need is a high road consisting of vectors we already know. So this could be QA plus AC if only we knew what the vector AC was. Now, if we knew the vector AB, we could take 1/3 of it, and that would be the vector AC. So, do we have a high road for the vector AB? Well, yes, of course we do. It's vector AQ plus QB, which is minus little a plus little b. You'll remember that minus a is the inverse of a, and that's what we need since we're going backwards along the a vector. So now we have AB equals AQ plus QB, which is minus a plus b. But we know vector AC is 1/3 of vector AB, so vector AC must be 1/3 of minus a plus b. Going back to our equation that QC equals QA plus AC, we can substitute this last expression for AC and we get QC equals A plus 1/3 of minus a plus b. Multiplying out the bracket gives QC equals A minus 1/3 of A plus 1/3 of B, which with a bit of simple fraction work is 2/3 of A plus 1/3 of B. And that's it. The vector QC, the one we're after, is 2/3 of A plus 1/3 of B. If we wanted, we could now factorise this expression by taking out 1/3 as a common factor and getting 1/3 into 2a plus b. And again, if we wish, we can write all of this as just one big fraction, 2a plus b all over 3. Again, at the risk of getting really boring, you can see how close this is to normal algebra. No wonder it's called vector algebra. We'll be using these ideas quite a bit in the section on vector proof, and you may already have a pretty good idea of where we're going with this from the simple example we've just covered.